let's talk about CNN. CNN stands for Convolutional Neural Network. It's one of the first neural network architecture that was proposed by Jan LeCun and used for the purpose of recognizing digits in the postal mail letters. Later on, it was extended to recognize objects in the images. So let's understand how it works. For the purpose of explanation, I'm using images here, so that it's easier, so that it's visual and it's easy to understand, to recognize objects in the image. But the same architecture can also be used for recognizing text and text classification. So CNN is used for image classification, as well as it can be used for text classification. So in this particular example, we have an image of a scenery where you have a boats, grass, and a lot of images of residential places right and behind the lake, right? And what we want to recognize is, we want to recognize if there are any objects in this image like dog, boat, bird, or a cat, right? So this is the input image, and the output we want to recognize is output we want to recognize is whether there is any dog is present, cat is present, boat is present, or a bird is present with certain probability, right? So in this particular example, the boat is present, so the probability of boat is higher, about 0.94, and the rest of the probability is lower. Okay, so the way it works is, what we do is, initially we create a list of kernels, also called as the convolution filters. So those filters are there. Those are basically filters of the smaller size, let's say 5 by 5, 7 by 7, and and there are several such filters. What we do is we convolve these filters with the original image, where we slide using the sliding windows. We take the element wise multiplication. We take a smaller subset, let's say the convolution filter size is 5 by 5. What we do is we select the 5 by 5 size of an image, then convolve this filter. The convolution operation is nothing but element wise multiplication of each element of this matrix here into this, right, into with this kernel filter, and then you take sum of that. That's a convolution operation. So there are several such filters that are used. So the intuition behind this is, we want each filter to recognize a certain characteristics of the image. Like one filter could be used to recognize the edges in the images, other filter could be recognized to use the higher level objects and things like that. So the first level convolution filter just recognizes very basic elements. For example, edges. One filter could be used to recognize a vertical edge, other filter could be recognized to use diagonal edge, other filter could be recognized to use the horizontal edge, and things like that. Then we do a pooling operation, where we retain only the most important information and ignore the least important information, right? Then we just stack these operations. We again convert another set of filters to learn a little bit higher level of features. So the first convolution learned about the edges. The second convolution can learn about higher level objects, right? Let's say it can learn about the water, or it can learn about the individual colors and things like that, right? So again, we keep stacking those elements and hierarchically learn the features. So the first layer learns edges, second layer learns color. There could be another layer that could learn the objects like boat and cars and things like that, right? So we stack together this convolution layer to learn the features in a hierarchical manner. The convolution layer at any stage uses the layers behind to learn from those layers. So hierarchical learning happens in this particular case. And the last layer here which is a fully connected layer, which is nothing but multi-layer perceptron, and this does the classification. The purpose of this is to do the classification into these individual categories. Right, so this is how the convolutional neural network works, and the ReLU function is basically a rectified linear unit. It is used for eliminating the negative values, only retain the positive information. Let's look at this more visually. So here, let's take example of a car. We want to recognize the car as it passes through multiple convolution layers. As you can see, the first convolution layer learns about few edges, right? Then the ReLU is used to retain only positive information and forget about negative information. The next layer of convolution layer again learns about few other properties of this image based on the previous convolution layer, and then we just keep stacking this convolution layer one after another till it learns more and more about the higher level features from the lower level features, and finally we pass it through a fully connected layer where it recognizes the objects. Let's look at another example. Here is an example where we recognize the face. So we start from the bottom to top. So the first layer, layer 1, recognize the edges of in the image, like diagonal, horizontal, vertical, all the edges it learns. Second layer, it learns the parts of the faces, right? Like it learns eyes, it learns ears, it learns lips, and the layer 3 then learns about the actual faces. So as you can see, this is what is called is the hierarchical learning, and that's the main pivot or the main learning point of convolution layer. So using this hierarchical learning, convolution can really learn a very complex patterns in the images as well as text. Okay, a convolution is nothing but element wise multiplication and sum. So let's take the example of this matrix. Okay, so it's a 5 by 5, 1 2 3 4 5, 1 2 3 4 5, and it has a value like this. And we convolve with a smaller element wise multiplication, 1 0 1 0 1 0 1 0 1. This will give you output of 4 3 4 2 4 3 2 3 4. Okay, so what we do is so this is a smaller filter that we select. This is called a kernel, this is called input, and this is called output. So what we do is this kernel is 3 by 3, so we first select this 3 by 3 area here. Okay, then we multiply each element of the kernel with each element of input, and then we sum it and then give the output. So in this case here it will be 1 into 1 plus 1 into 0 plus 1 into 1 plus 0 into 0. So you just keep doing element wise multiplication, blah blah blah, and this gives us 4, right? So and then you do it. Once it is done, then you slide the kernel to the next 3 by 3 window like this, and then continue the process. Let's look at it more visually in the PowerPoint. So this is the kernel convolution operation that is explained visually. So you can just slide the kernel from left to right and then from top to bottom, and then calculate the output feature, right, as it is shown here. Right, so you can also see the convolution also results in a smaller matrix to make the input and the output of the convolution same. Generally we prepend pad this matrix with the zeros on each side, and then we apply the convolution. Then in that case the input and the output size remains same. So that is typically called a padding exercise. So that otherwise, as you keep applying the convolution operation, your matrix size will go down all the way to 1 and 1 to 1. So you wanted to avoid that operation. We first inflate the input size matrix by padding zeros, and then we apply convolution so that output matrix will remain same as input matrix. Sometimes we have to add 1 rows in padding, or sometimes we have to apply 2 rows depending on the size of the matrix and the size of the kernel. So this is about convolution. Let's learn about the ReLU. The main purpose, so ReLU is nothing but it's called rectified linear unit, and let's say if this is x, this is 0, this is 5, 10. The ReLU function looks like this. So here ReLU of x will be equal to max of 0 or x. This is how it is defined. So once you apply this ReLU function, basically what it does is it eliminates all the negative values in the function and it keeps only the positive values. So here is an example. This is the input feature map. When you pass through a ReLU function, it eliminates all the black negative values and we keep only positive values. So this is how the rectified linear unit works. So after the rectified linear unit, the next operation what you saw was the pooling operation, right? So let's learn about the pooling operation. So the pooling operation is nothing but is used for retaining the most important information and removing the least important information. So let's say the output of ReLU function is something like this: 3 by 3 matrix. Okay, then there are several types of pooling we can do. The max pooling, which basically takes only the maximum of all these values and will keep these values, right? Then sometimes you also use the average value, which does the average of all these values and it will do the average value in this particular case. So you can take the average of all this and put it here. It's around 6.9, right? Or you can do min pooling also, which will be 3. So the goal of the pooling operation is to just retain most important information, right? So for example, if this is happen to be an image in 10 pixels, maybe the pixels below certain values doesn't have, we don't care, we only keep the most important pixels and then we just use that over here. So this is how the pooling operation works. Another way to understand convolution is to look at visually how it applies to the image. So for example, here it's an image, right? So, and this is the kernel that can be applied to the image to see the output. So let's see, if you want to blur the image, you can apply this kernel and you can see the image is smooth. A blur kernel is nothing but you apply this kernel and takes the average of all the pixels. Then if you want to see the outline of the image, you apply this filter, which results in taking only the difference in the image pixel intensity. It highlights that. Similarly, you can look at Sobel operator to get other effects, right? Sharpen, then this is emboss. This gives you a 3D effect. So as you can see, by applying kernels, you can get much more interesting features. And this is all a convolution. So once after the convolution, so far, just want to go back to the original CNN architecture. You saw that we looked at convolution, we looked at ReLU, we looked at pooling. So we stack these layers one over another to learn the individual features in the image hierarchically. And the last layer is a fully connected layer which is responsible for the actual classification. So that is this layer, right? So this layer basically, as you can see, is just a multi-layer perceptron. The multi-layer perceptron, and it's fully connected layer that looks something like this. Right, a multi-layer perceptron is nothing but you have nodes here, 5 nodes, and let's say you have a hidden layer, and then you have an output layer, right? This is how multi-layer perceptron looks. And when you say fully connected, basically each node is connected to each next layer. That's what it means. And you just create this perceptron, right? And these are the output, and you learn. So this is the input, this is the hidden layer, and this is the output, right? So you will use a multi-layer perceptron along with the softmax function, which calculates the probability of the output nodes and classify them. So this multi-layer perceptron, you basically learn the weights on the layer by giving a supervised data. And this multi-layer perceptron, basically what it does is it uses a supervised learning process where it learns these weights. Then it knows for a given image it's already classified into certain categories. Initially we randomly initialize these weights, then and let's say initially for the first few iterations the neural networks does a wrong prediction, but then it calculates the error and it propagates. We do a forward propagation and it predicts the output, right? And then we calculate the error between predicted output and the actual output, and then you propagate it back, and you keep adjusting the weights until the output is correct. So the neural network uses forward and the backward propagation to learn the weight, so that the error between predicted output and actual output is as low as possible. And in the process it learns to classify each output with a certain probability. The higher the probability, then that object we say is the right object in this particular example. So these are the fully connected layer works. So you saw how the CNN works for images. Now for text, the method is exactly same. The only difference in this particular case is instead of 2D array of pixels, here we use 1D array of words, right? So in case of CNN, for text, what we do is we have words, right? Each training example is nothing but a sequence of words. So, and these are the embeddings, right? We calculate the embeddings of these words by using either globe, word2vec, BERT, fasttext. Basically the embedding is nothing but process of converting words into numeric vectors, right? And then what we do is we select a kernel and again convol to give the output, right? So let's take an example. So let's say we have the embeddings that look something like this. Let's say 1 3 3 0 1 2, and we have a kernel that something looks like this, 2 0 1. Then the output will be 5 6 7, and let's explain how. So what we do is, this is 3 by 3 kernel. So first we select these 3 embeddings, then we select this kernel and then do element wise multiplication. So 1 into 2 plus 3 into 0 plus 3 into 1, that gives me 5, right? then once then so this is then we put it here. So what we do is we multiply this with this, we multiply this with this, we multiply this with this, and then calculate this, right? Then we repeat the process. The next window that we do is from here to here, right? And then we keep repeat, and then we again calculate, then we again multiply this with this, we get 6. Then we select next window, which is from here to here, and then last window from here to here, and then calculate other two elements. So this is how we use convolution for text. So the process remains same, but here in case of 2D array, we just use a 1D array. So in case of text, instead of we call it as a 1D CNN process. So just like in images, the CNN learns the hierarchically learns to detect edges in the images. Also, it learns to detect the higher level objects like the parts of the face and then the face. In Word, basically it learns, in case of text, it learns the relationship between the words, right? So it is said that the words with a similar meaning quite often occur together, and we can say, like for example, if you want to extract the relationship between W1, W2, W3, we can learn by applying the filter, we can learn those features, right? And these features are learned by the convolutional neural network on the fly. It will start with random weights for this convolution filter, and then it calculates certain output. Of course it is wrong initially, but it calculates an error and keeps readjusting the weight until the filters are correct. So in the process, it learns this convolution filter with the proper weights, and each convolution kernel characterize a specific features of the text, in this particular text as well. So you can calculate how much word 1 and word 2 and word 3 are correlated. Then it calculates how much word 2, 3, 4 and 4 are correlated. And it uses exactly same convolutional neural network. It has kernels, it has the pooling, it has the fully connected layer, and the process remains exactly same. The only difference between text and images use 2D convolution, whereas text at word level it uses 1D convolution.